I will say one of the college classes I had, there wasn't a full class of us. I think there was about 6 to 7 of us in the class. And we ended up, big full class, I think it was, I can't even remember how many seats, but we always ended up sitting in the same spot the whole year. And one of our classmates came in and like, we're going to mess with one of the guys. She moved one desk forward. He came and saw her sitting where he normally sat. So he came up from behind her, took the desk that was behind hers, moved it in front of hers and sat down. Because he always sat in front of her. The only thing that made it funnier was when the professor came in and was trying to figure out why there was an empty spot where a desk used to be. Because there was no assigned seat. We just sat that way. So, what we're doing today is finishing up the notes. I think for the most part, we had a good grasp of what we did yesterday. Our horizontal translation, left, right, up, down, and reflections. Now, y'all have this written down already? And if not, I think, yes, lines, linear. So linear, quadratic, absolute value. I think I might have had it in a different order, but we have these three here. Now the general versions or equations for these here, for the equation of a line, f of x is equal to a times x minus h plus k. Our quadratic, f of x is equal to a, parentheses, x minus h squared plus k. And absolute value, f of x is equal to a times the absolute value of x minus h plus k. So we had these three here. Our h is our horizontal translation. It is our left or right movement. It's how far the function is going to move to the left or move to the right. Our k is our vertical translation. It is our up and down. And the last one we had yesterday was dealing with a. If it is negative, specifically the sign, if the value or the number where a is negative, then it is a reflection across the x-axis. If a is negative, then it's a reflection across the x-axis. And those are the three we had yesterday. Yes, and we felt comfortable with this and how they work and how we applied them to the function. We have one more we're going to apply, and it is dealing with a again. I had someone during fourth hour ask if we can use a different letter than A, but it's more, A has different parts to it. If it's negative, specifically negative, it's a reflection. Now, if A is greater than 1, if the number is greater than 1, we say that it has a vertical stretch by whatever that amount is, a vertical stretch of 2, or a vertical stretch of 3, or a vertical stretch of 98. It is telling us how much we're going to stretch or increase the function by. It's how much it's going to increase faster or slower. Now, if 0 is less than a is less than 1. If
May I have your attention, please? It is now now time to release the softball girls to go to the field house at this time. Thank you.
So, yes, the homework numbers are up there already, so y'all can get those. The video will be posted up shortly. I'll have it up there hopefully before the end of the day. Good luck. Now, if the value is between 0 and 1, it's a vertical shrink. So if the number value of A is greater than 1, it's a vertical stretch. If it's between 0 and 1, it's a shrink. And we're looking at the number, not the sign. Because if it's negative, it's a reflection. But if the number is greater than 1, it's a stretch. If it's between 0 and 1, it's a shrink. So questions on this here. Now, this isn't the textbook definition of vertical stretch and shrink. The textbook definition has one more piece to it. You do not have to write this. And the only thing that the textbook definition adds is absolute value. If the absolute value of A is greater than 1, it's a vertical stretch. If the absolute value of A is between 0 and 1, it's a vertical shrink. That's just because if the A value is -2, the negative is not a part of the stretch or shrink. That's why they add the absolute value. So we're just looking at 2, which would be a vertical stretch. But I think we are at a level that we can differentiate between the negative and the number. So we don't necessarily have to look at that there because the negative is attached to the reflection across the x-axis. That's all the negative tells us. If it is not negative, there is no reflection. It's just a stretch or shrink. Now, if A is 1, there is no stretch or shrink. It's just the function itself. Now, the next slide that we had is this here. Another way to transform the graph of a function is to multiply all the y coordinates by the same positive factor, other than 1. When the factor is greater than 1, the transformation is a vertical stretch, which we just said. When the factor is greater than 0 but less than 1, between 0 and 1, it's a vertical shrink. Now, in the last few hours, I did some examples of this here. Let's clear that out. So we'll deal with x squared again. So vertical stretch, the value of A, the number in front of the x outside the parentheses has to be greater than 1. Someone give me a number greater than 1. 7, 2, we'll do both. We'll have both of them up there. So we can say 7, and our x is right next to alpha squared graph. So the one in blue is the parent function, and the one in red is our vertical stretch. We can see it's increasing faster along the y. The y values are increasing faster. That's our vertical stretch. We're stretching it vertically. Now, if we look at a table, second graph, so when x is 1, the y value is normally 1, and the new one is now 7. It's increased by a factor of 7. When x is 2, it was at 4, now it's at 28. You can see each one is increased by a factor of 7. Now we could say 2. Let's add both. 7x squared. So the one in red is now 2. The one in black is 7. Well, we can see that they are still increasing faster along the y. One's increasing faster than the other. Yes? So that's vertical stretch. Vertical shrink. Someone want to give me a number between 0 and 1? A number between 0 and 1. 0.8. So, because we're looking for pretty much most decimals, so 0.8 squared is this here. So if we look at the table, the one in purple is our vertical shrink. So at 1, originally it was 1. Now it's 0.8. At 2, it was supposed to normally 4. Now we're 3.2. It is increasing slower. We're stretching it out. It's increasing at a slower pace. It shrank down. Now, I'm going to switch it to 0.2. Now we can see the dramatic change. And if we look at the graph of it, we can see that it's a lot wider because it's increasing slower. Does that make sense? Okay. Now let's look at our first example. T of x equals 2 times the absolute value of x. Well, what's its parent function? Absolute value. So I'm going to write the parent or the general version of this function here. Now, as I said before, you don't have to write this out every single time, but if it does help, write it out. A times x minus h plus k. Well, we have no h value and we have no k value technically. Well, technically we do, but here, are we adding a number to it? No, so the actual value of h is 0. So there is a value there, but it doesn't do anything. We're not going to list it. We're not going to say that it has a movement of 0 units up or 0 units down. It's technically the same, but there's not a whole lot of reason to it. I've used this analogy all day today, and I think it lines up about right. You'd be asking, like, what did you do yesterday? Well, I didn't go to Walmart. Okay. I mean, that doesn't mean anything, does it? No, I didn't go to Ireland. After about one or two of those, you'd be about done with the conversation and going to walk off. That's a little odd to say those statements. And it's the same thing here. If it's not there, we're not going to list it. There's no reason to. But we do have a value for A. Our value for A is 2. So that tells us that it's either a vertical stretch or a vertical shrink. And this indeed would be a vertical stretch of 2. Since the value of A is greater than 1, it's a vertical stretch. If the value of A is between 0 and 1, it's a shrink. And if that number is negative, then it's a reflection. Since this is just positive 2, there is no reflection. It's just a vertical stretch of 2. Questions on A before we look at B. B, h of x equals 1/2 x squared. What parent function does it belong to? Quadratic. F of x equals a times x minus h squared plus k. Well, we don't have an h or k, so it's not moving left, right, up, down. But we do have a value for a, yes? And its value is 1/2. And this will be a vertical shrink of 1/2. Because 1/2 is between 0 and 1, it's a shrink. It's a vertical shrink if the value of a is between 0 and 1. It's a stretch if it's greater than 1. If the a value is negative, then it's a reflection, plus whatever a is. We feel good about A and B. Are you ready for number 5? Number 5, what parent? What's its parent? Linear. Because it is an equation of a line. Number 5 would be a vertical stretch because our value of a is what? 3. It's greater than 1. Because whenever a is greater than 1, it's a stretch. Whenever it's between 0 and 1, it's a shrink. Questions on this here? We good? Yeah. Vertical stretch of 3. And we always put the amount that it's stretching by, or the factor that it's stretching by. So here the factor is 3, because we have a is 3. Questions on any of this so far? So we can look at the next one, which is quadratic. F of x equals a times x minus h squared plus k. Well, for this one here, a is a fraction, yes? So it has to be a shrink, right? No. Why not? It's an improper fraction. It's still greater than 1, yes? And again, it is sometimes tempting, if we're not paying attention, fraction, shrink. We got to make sure, is it greater than 1 or between 0 and 1? Here it is, greater than 1. So this is a vertical stretch of 3/2. Now I will do that every now and then just to make sure we're on the same track or paying attention. Because again, I've had some students in the past, because it's just a fraction, they immediately think shrink. But here, the fraction is greater than 1, so it is a stretch. And if you're not sure about a fraction, if it's greater than 1, less than 1, turn it into a decimal. That's one way to check. Or is the bottom of the fraction smaller than the top? Is the numerator bigger than the denominator? Is the top bigger than the bottom? Then it is greater than 1. If not, it is less than 1. And lastly, absolute value. Well, we don't have h and k again, but we do have a value for a, which is 0.2. Is that between 0 and 1 or greater than 1? So it's a vertical shrink because it is between 0 and 1. Questions on any of this here? We feel good with these so far? Awesome. Now, you might be wondering at this point why I've been rewriting the whole statement, whole equation each and every single time. Because here, all we've had is vertical stretch. So couldn't we just write a times the absolute value of x, or a times x squared? I mean, yes, but not every single one is just going to have a transformation. Because if we look at this next one here, we have 2 times the absolute value of x plus 1. Which is an absolute value equation. Because if it asks to identify the family, some of the problems will ask you to identify the family it belongs to. So this is absolute value. But we do have values for more than just one of our a, h, and k. This one here, we don't have a value of h, which means there is no movement left or right. But what direction do we have a movement? We have up and down. How far are we moving up or down? So it would be 1, because it is our plus 1. And are we moving up or down? Up. Because that's the one nice thing with our vertical translation, is exactly what it looks like. Since it said plus 1, we're moving up 1. If it was minus 1, we'd be moving down 1. That one's nice. It's the left-right. Inside those parentheses are absolute values, is what's flipped. Now the other one is the 2, yes? It's taking the place of a. So the 2 would be a vertical stretch of 2. And we know it's a stretch because the value of A is greater than 1. It's a vertical stretch. Now that value of A is positive, which means there is no reflection across the x-axis. To have a reflection across the x-axis for this, it would have to be -2. The negative attached to A gives us the reflection. The number is our stretch or shrink. We get that distinction? Yeah, and it's one of those things I try to put an emphasis on because we have two things attached to the same spot. So it's making sure to deviate between the two. Because I'm not going to name names, but I have seen assignments or tests turned in that said it had a vertical reflection across the x. Or yeah, it's like, okay, I get it, because it's easy to get those two. They are connected and flipped. But again, negative is reflection across the x. The number gives us the vertical stretch or shrink. Here, our g of x is 1/4 x minus 3 squared. Its family would be quadratic. Well, this one we don't have a value of k. So that means it's not going to move where? Up or down. Our minus, so our x minus 3, our minus 3 or inside tells us that we are moving which direction? Not quite. Because inside is left or right. So we're moving 3 units to the right. Because again, our left-right moves kind of the opposite of what we think. Because x minus 3, the minus 3 looks like it should be going left, but it's actually going right. Now, we delved a little bit deeper into that, especially yesterday, because the formula is x minus h. The x's here line up, the minuses line up. So really the value of h is positive 3. That's why we're moving right 3. But it does look negative. So sometimes instead of trying to keep all that straight, minus 3 is moving to the right, plus 3 would be to the left. Does that make sense? So either way, we'll have to kind of keep it straight. And the last thing we have is what? The vertical shrink of 1/4. That 1/4 is in the place of A. And since it's between 0 and 1, a vertical shrink of 1/4. Now, because the 1/4 is positive, there is no reflection. So the only two transformations for this here is a right 3 and vertical shrink of 1/4. That's it. Questions on this here? Are we ready for the last two? Yes, both of them are. So this one here, well, is absolute value. Well, we have something that is taking or has a place for A, H, and K. We have all three, yes? Where do we want to start? Doesn't matter, y'all pick. Up, down, left, right, or it's going down. So we have minus 3. So that indeed would be down 3. Because the nice thing about up and down is exactly what it looks like. Since we have minus 3, it is down 3. And then left, 5. Since it's plus 5 inside, opposite what we think. So instead of plus to the right, it's going to the left. Because the value of h for this here really is negative 5. Because negative 5 would give us our plus. or just the opposite. Instead of going right, we're going left. Yes, and since the A is negative, we have a reflection across the x-axis. Reflection across the x-axis. Figured out how to type it in. The absolute value is not too bad because it's math over 1 to none. But we have this here. And that's it. Questions on this here. Now again, I said yesterday, and I will say this again and again, having a precise knowledge of how to graph is great, but it's not so much necessary, especially with the calculators we have. The main reason I do this is so that we get an idea. We have a picture of what's going on. Now, graph, this is the parent function. So you can draw this if you want. I'm just putting this down here. So we have this here, yes? Because we have that idea. Now from this here, from our transformations, we're saying that we moved this parent function down 3, left 5. Or left 5, down 3. 2, 3, 4, 5. So that's our down and left. Yes? And then we flip it, yes? So it's going to be going down. So something like that there. Equals. Let's put I'll put the absolute value back in there. Negative absolute value of x plus 5 might need the minus 3 graph. So I have an idea of what it looks like. And that's the key, because we've solved equations before. I don't quite remember if we solved absolute values in Algebra 1, mainly because it's been a few years since I've taught it. But if we're solving, we're trying to see what's going to make this equation be 0, where it's going to cross the x-axis, yes? What is that one that we just drew cross the x-axis? Or does it? Well, no, it's going down, right? It's never going to cross the x-axis, which means there is no solution for it. There is no value of x that will make that be 0. Well, did I have to do any calculations? Well, no, because we have an idea, and we can see the picture of the graph, the general picture, not the exact. We don't need the exact. But I can get a good enough understanding of how the function is behaving to get an idea of what it should behave like. And that's the nice thing about this. Because if we can get a general picture, it'll help us start. That way, when we start getting solutions, do they line up with that picture? If they do, awesome. If not, something's up. But that's the whole reason we do this here. Last one. This one is quadratic. We have 3 transformations. Let's start with the plus 4. Up 4. Now there is no left-right movement because there's no sets of parentheses with something adding or subtracting x inside. But we do have the negative 0.25, yes? So the 0.25 is between 0 and 1, so it is a vertical shrink of 0.25. The negative is the reflection. So the negative is purely attached to the reflection. It has nothing to do with the stretch or shrink. That's why the textbook definition of stretch or shrink is if the absolute value of A is greater than 1, then it's a stretch. If 0 is less than the absolute value of A is less than 1, then it's a shrink. because that negative is not attached to it. It's purely attached to the reflection. And that's it. Does that make sense? So really, we can have a reflection across the x, a stretch, a horizontal translation, and a vertical translation all at once. We can have multiple things going on. And even though we haven't done it in these here, I mean, we could technically have a movement of up 7.5. It's possible. I can have a vertical stretch, not string, vertical stretch of pi. Possible. But we're going to stick to our rational numbers for the most part. That's it. That is the end of 1.2. So the homework problems are 3 through 5, 9 through 15 odd, 19 through 25 odd, 27, 28, 31. Now, some of these problems here will say graph the function. Have we graphed anything at all today? No, don't graph. Unless I specifically ask you to graph something, just don't assume that I do not want it graphed. And that's normally the case. If you do have a question, email me, ask me, let me know. But here, do not graph any of these. If you want to use a graphing calculator, Desmos online, desmos.com will graph. So if you want to plug them in and check and see if it is doing what it's doing, or if you have a graphing calculator, you can plug it in there and look at it and see. Those work. All right? Just a way to make sure it is doing what you expect it to do. So 3 through 5 is just give the parent name and then its transformation. So it's 3, 4, and 5 for that one there. 9 through 15, just describe the transformation. As it says graph, so not having a graph, just describe the transformation. 19 through 25 odd, describe the transformation. 27, 28, 31, describe the transformation. That's it. All right. So the only ones that are odd for these two is 19 through 15 and 9 through 15 and 19 through 25. We're still doing 3, 4, 5. Does that make sense? So the only ones that are odd or even will be the ones that specifically are in front of odd or even. The rest are all. But that is all we're doing today.